So, a machine the size of an entire factory floor just quietly powered up inside a locked lab in Shenzhen, and depending on who you ask, it either flips the whole semiconductor game on its head, or it's a very expensive science project that goes nowhere. I've been buried in this story for a while now, and honestly, it's way more interesting than either of those hot takes, because the thing China built here isn't a copy of ASML's machine. It's a completely different bed, and I think that's the part almost everyone is glossing over. Stick with me because I'm gonna walk you through exactly how this thing works, where it's genuinely impressive, and where it still faceplants. And if you're into this kind of breakdown, where I actually explain the physics instead of just shouting headlines at you, do me a favor and tap subscribe real quick, because this channel runs on people like you hanging around for the whole story. Okay, let's get into it. Let me set the stage, because the why here is the whole point. Modern chips, the ones in your phone and in every AI data center on the planet, are printed with light. You take a silicon wafer coated in light-sensitive chemicals and shine a pattern onto it, over and over, layer by layer. The catch is that the smaller you want your circuits, the shorter the wavelength of light you need. And to get down to the really advanced nodes, 7 nanometers and below, you need extreme ultraviolet light with a wavelength of just 13.5 nanometers. That's not a small step down from regular ultraviolet. It's a monster of engineering problem, and for years, exactly one company on Earth could pull off this in a factory: ASML in the Netherlands. That monopoly is the reason we're even talking about this. Back in 2022, the US effectively blocked ASML from selling EUV machines to China, and the logic was simple: no EUV, no cutting-edge chips, no way to catch up in AI. So China was left trying to build a 7 nanometer and 5 nanometer class chips using older, less precise machines and squeezing incredible results out of hardware that was never meant to go that small. What just happened in Shenzhen is China's answer to that wall. In December of 2025, Chinese industry reports and state media confirmed a homegrown EUV prototype had successfully generated a stable 13.5 nanometer beam and pushed it through a domestic optical system. First light, as the engineers call it. And I'll be upfront with you with my opinion here, because I think it's earned. Even as a prototype, this is a genuinely impressive piece of work, and I don't think the doubters give it enough credit. Here's where it gets fun though, and here's the part that got me hooked. ASML and China are making the same 13.5 nanometer light in two totally different ways. ASML's method is called laser-produced plasma, or LPP, and it's borderline insane when you really look at it. Inside the machine, a generator fires a stream of molten tin droplets across a vacuum chamber. Until recently, that was around 50,000 droplets every second, and ASML is now doubling that toward 100,000 per second in its newest systems. Each of those tiny droplets, while it's flying through the air, gets hit by a powerful carbon dioxide laser. Actually, two pulses, one to flatten the droplet into a pancake and one to vaporize it. When the laser strikes, the tin explodes into plasma hotter than the surface of the sun, and that plasma spits out EUV light. 50,000 times a second. Every droplet hit dead center mid-flight with lasers timed to the nanosecond. When people say ASML's machine is one of the most complex objects humans have ever built, this is what they mean by that. China, on the other hand, went a completely different route with its prototype, and this is the clever part. Instead of LPP, the Shenzhen and Harbin teams leaned on a method called laser-induced discharge plasma, or LDP. Rather than shooting thousands of flying droplets and trying to snipe each one out of the air, LDP uses tin coated onto rotating electrodes. You vaporize a bit of that tin, then hit it with a high-voltage electrical discharge, and the electron-ion collisions in that discharge produce your 13.5 nanometer light. I personally think this is a very smart move. Really, you sidestep the whole nightmare of hitting 50,000 moving targets a second, and the architecture is mechanically simpler, smaller, cheaper to build, and crucially, it draws less power. When you're starting from scratch and you're locked out of an established supply chain, picking the simpler path is exactly what you should do. Now, the honest catch is that LDP has always had one big weakness, and that's power. Earlier discharge plasma sources topped out at around 30 watts, which is, well, nowhere near useful. China's current prototype is reportedly running somewhere between 100 and 150 watts. That is a huge leap from where this technology used to be, but for comparison, ASML's commercial machines already run around 600 watts of EUV power at the source, and just this year, ASML demonstrated a pre-production light source hitting 1,000 watts in a lab near San Diego, with a stated path towards 1,500 and even 2,000 watts down the line. Power matters because it decides how many wafers you can push through per hour, and throughput is basically the whole business model. So yes, China got the light, but there is a big gap between getting the light and getting enough of it to run a profitable factory. Okay, so you've made your UV light. Now you have to actually aim it, and this is where things get brutal in a way most coverage skips right over. Here's the problem. UV light at 13.5 nanometer is so energetic that regular glass lenses just absorb it. The light goes and never comes out. So you can't use lenses at all. You have to bounce the light off of mirrors. But not normal mirrors either, because even a polished metal mirror soaks up EUV. The solution is genuinely wild. You stack dozens of alternating layers of molybdenum and silicon, each layer only a few atoms thick, and that stack reflects EUV through a quantum interference effect. These are called multilayer mirrors, and they have to be smoother than almost anything else humans manufacture. We're talking a surface roughness of around 50 picometers. To put that into perspective, if you scaled one of these mirrors up to the size of Germany, the biggest bump on the surface would be a fraction of a millimeter. And for decades, one company has owned this art form, Zeiss in Germany, ASML's optics partner. So how did China get around Zeiss? Well, this is the part that I find really telling. Chinese institutes, especially Changchun Optics, actually produced their own multi-layer mirrors and integrated them into the prototype. But their mirrors don't reflect as efficiently as Zeiss's, and every mirror bounce loses light. When you have several mirrors in a row and each one is a little leaky, those losses stack up fast. So how do you compensate? You go bigger. You use larger collectors to gather more light, longer optical paths, and a much bigger overall machine. And that, right there, is why China's prototype fills a whole factory floor while ASML's system is roughly the size of a school bus. That giant footprint isn't a flex, it's a workaround. They're brute forcing with size what they can't yet match in precision. Is it elegant? No. Does it work well enough to make light land on a wafer? Apparently yes, and I'd agree that that's the more important question at this stage. Now let's talk about a problem you can't engineer your way out with clever design because it comes out of the ground, and that problem is helium. EUV fabs drink helium. It's used for cooling, for creating inert environments so nothing contaminates the process, and for leak detection across the machine. An advanced fab burns through thousands of cubic meters of this stuff every month, and there's basically no substitute. You can't synthesize helium. Once it escapes into the atmosphere, it's gone for good, and here's China's exposed nerve. It imports more than 85% of its helium historically from both Qatar and Russia. Its own natural gas reserves barely contain any, so domestic production covers less than 15% of demand. Then, 2026 turned it into a perfect storm. Qatar's main helium factory got hit and supply dropped. Russia slapped on its own export controls, and in July, China responded by banning helium exports entirely to keep whatever it has for its own industry. When you're trying to build a technology that guzzles a resource you mostly have to import from countries in the middle of overlapping crises, this is a serious strategic weakness, and no amount of engineering brilliance fixes it overnight. And helium is just the headline example. There's the photoresist chemistry, the pellicles, the mask blanks, the whole ecosystem of consumables that ASML supply chain refined over 20 years. A prototype proves the physics. It does not prove you've built the boring, reliable industrial supply chain underneath it. That is a different mountain to conquer entirely. Now, I want to give credit where it's due because machines don't build themselves. A big reason China moved this fast is talent, and specifically talent that came home. The team that developed China's LPP light source, the ASML style approach, is reportedly led by Lin Nan, who used to head light source technology at ASML. Just think about that again. A person who helped run ASML's core technology is now working on China's version, and he's not alone. Huawei and its partners have hired chip industry veterans with experience at Applied Materials, Lam Research, KLA, TSMC, Intel, and ASML itself. On top of that, Chinese research publications on EUV-related science have surged since around 2020. This wasn't luck. It was deliberate, it was funded, it was a coordinated national push, and whatever you think of the politics, as a piece of industrial strategy, I have to respect the sheer focus of it. Now, let me bring it home with a reality check, because the honest answer sits right in the middle of the hype and the dismissal. This prototype is a real milestone. It's not a production-ready piece of equipment. Those are both true at the same time. For context, ASML took roughly 12 years to go from its early EUV prototypes to a tool you could actually put on a factory floor and trust. 12 years. So anyone telling you China is about to flood the market with EUV chips next quarter is not being straight with you. Turning a working prototype into a reliable, high-volume factory equipment, machines that run day and night with predictable yields, is arguably harder than the first breakthrough. But, and this is the key insight that I really want you to walk away with, China doesn't need to beat ASML. It doesn't need to match ASML's throughput on its performance. It just needs something better than they're using now. Right now, China's leading foundry makes advanced chips with older DUV machines using a trick called multi-patterning, running the same wafer through multiple exposures to fake finer detail. It works, sure, but yields are often below 50%, which means a lot of expensive scrapped wafers. If a homegrown EUV machine, even a slow, power-starved, oversized one, can beat that number and cut reliance on tools China isn't allowed to buy, then it's a strategic win regardless of whether it ever embarrasses ASML on a spec sheet. That's the bar, and that's a much lower bar than the headlines imply. And here's my honest take, wrapped up. This isn't the moment ASML's monopoly ends, but it might be the moment it stopped being permanent, and that is a real shift. China proves the physics work on its own terms, with its own light source, its own mirrors, and its own engineers. Everything left, the power, the yield, the supply chain, the size, and its engineering is just a grind. And if there's one thing this whole saga has shown, it's that a grinding, funded, focused effort tends to get there eventually. I find that genuinely fascinating to watch, and I'm oddly optimistic that the competition pushes everyone to build better machines. If you got something out of this, smash that like button because it honestly helps more than you think, and subscribe so you catch the next one when China's prototype takes the next step, because trust me, this story is far from over. I'll see you in the next video.